We will now start. It will be a demo on experimental evaluation of algorithm-assisted human decision-making and an application to pretrial public safety assessment. And it's my pleasure to introduce Kosuke Imai, who's from the Department of Government, Harvard University, and he will be followed by James Greiner, also from the Harvard Law School. Thank you, Kosuke. Can you share your slides and start?
Yeah, actually, well, thanks for this opportunity and introduction. Actually, we're going to have Jim starting off, so I'll let him take over.
Terrific. Can everyone see the slides? Think so. So thank you so much for the opportunity to speak today. My name is Jim Greiner. As I just mentioned, I'm a professor at Harvard Law School and also a statistician, but more a lawyer by trade. And I am here to set the stage for the work that we're doing in our team today. And so the basic challenge is with respect to human and machine joint decision making. There's in big picture, there's a continuum or a spectrum of the ways that human beings and machines can interact in making a decision. You can imagine an unguided human decision, which is how an awful lot of decisions are made, including extremely consequential ones these days. A machine-guided human decision, which is what we're going to be studying today, the contrast between the unguided human decision and the machine-guided human decision. But there are a lot of other ways that you can imagine the machine being more involved in the decision-making, including turning decisions entirely over to machines. There are debates occurring in numerous social settings, including anything from self-driving cars and parlor games. Popular way of doing things for various reasons that I might get a chance to discuss is the one that we'll talk about today, machine-guided human decisions in contrast to just pure human decisions. And so there is strong evidence that has been around for decades, almost even a century at this point, that machines can outperform humans in certain decisions along certain dimensions. And so there have been certain spectacular examples of machines outperforming humans in popular parlor games. And there is some evidence, observational evidence, for example, that machines could potentially outperform humans in decision-making in certain highly consequential decision-making contexts in criminal law, which is going to be the application setting for this morning. This afternoon, where you are, specifically predisposition release. And I'll explain what predisposition release is in a moment. It's also true that machine-guided human decision-making, that model has been incorporated into a large variety of highly consequential decision-making in medicine and engineering, in human resources, human relations, and all sorts of other settings. One of the things that I have to urge my colleagues to do in the law school a great deal is to think counterfactually with respect to whether it's a good idea to involve a machine, in a decision that would otherwise be performed entirely by a human being. And that's one of the things that we'll be trying to emphasize during this work presented this morning is counterfactual thinking. This is counterfactual thinking at a sort of policy level, which is where at least part of the debate occurs in the circles in which I run in law schools. And it is a bit of a challenge sometimes to get folks to think counterfactually what would happen if we didn't involve the machines. So there is a lot of criticism of involving machines or data generally in decision making. And so one question to keep in mind, this is simply a typology, and the yeses and the nos are nothing special. It's not like I know what the answers are here. These are to be debated. But the point is to show what counterfactual thinking might look like in this policy type arena. What would happen if we involve the machine versus what would happen if we didn't? And this is, again, the sort of thinking that I think we need to be doing in the policy arena. And this is, again, what gave rise to this research. Let me move on here. As I mentioned, human-machine decision-making, the hybrid model, is popular, and machine-guided human decisions via something, including via something called a risk assessment instrument, is extremely popular. This is a basic way of presenting, at least, the construction of a risk assessment instrument that I use when I'm speaking to legal audiences. This will not be particular news to this particular audience. The idea of compiling data on some outcome that you wish to understand the risk of, and potential predictors that are observable earlier than the occurrence of the outcome, compiling data on those two items, using statistical techniques of varying degrees of sophistication to try to isolate good predictors, which need not be causal, and create functions of some kind associating predictors and outcomes. Then, and this is a key step that might not have occurred to this audience, at least in the legal field, you typically have to dumb it down. You typically have to reduce weights, if you're going to use weights or classification categories, to integer scores. Because if you don't do that, you will run into the problem of folks in the legal community for simply refusing to accept the idea. This is probably an overstatement, but the example I use to illustrate this concept is that the folks in the legal arena might be able to handle a score or a weight of a 1 or a 2, but not a 1.2. At that point, they'll simply say, this is not something that I understand, and therefore I'm not going to use it. And then occasionally, after you do the use of it, we might want to revalidate, in part because you think that perhaps behavior could change in response to the introduction of the risk assessment instrument. It's perhaps less likely in the setting we'll be discussing this morning, which is predisposition release. More likely, potentially, if, for instance, you were use this with police officer citizen interactions, risk assessment instrument in that context, where it is used currently. In the U.S. criminal law, as I mentioned, there are a variety of places in which machine-guided human decisions via risk assessment instruments are used. We don't use them yet with respect to the last bullet point there, guilt or innocence. That still is considered a third rail, something that we don't touch with machine-guided human decision-making. But we use it in a lot of highly consequential contexts in criminal law. And as I mentioned, we're going to be using it on a judge's initial decision to release an arrested individual, which again, I'll be talking about right now. What does that look like? What is a judge's initial release decision, which again provides the setting for the current application this morning. Basically, what happens is that a police officer encounters someone in public or executes an arrest warrant, but usually the former. It's really a police officer encountering someone in public, potentially either personally witnesses an offense or talks to witnesses who do witness an offense and decides to arrest someone, take someone into custody. So this is a custodial arrest. The individual is taken into jail and processed there, fingerprints and booking and that sort of thing. And under United States law, within a certain number of hours, the obligation of the authorities is to assess whether that individual can be released. And in many jurisdictions, not all, many jurisdictions, including the jurisdiction that provided the data and the setting for this particular application, this is done via an in-person live hearing in front of a judge or a magistrate or commissioner. These are various names that go for that judge. And there are various options that the judge has. The judge can do what is called own recognizance release, OR release, which is basically the judge saying, I'm going to release you, arrestee, with just simply a promise to reappear and not to do any dirty deeds while you are waiting the trial and disposition of your criminal case. But you don't have to put any money down, and there are going to be no particular conditions associated. In this jurisdiction, there is also something called a signature bond, which is basically a way of saying that I'm going to release you, defendant, but you have to promise that if you engage in some kind of misconduct, such as failing to appear or engaging in some kind of criminal activity, that you will pay us some money. Now, that promise to pay or that imposition of an obligation to pay is actually somewhat illusory. Most defendants in criminal justice are either indigent or so close to it that no one would waste their time attempting to collect on the money. So it really is basically a type of OR release, but there is at least a hint of an obligation, something that if you were to engage in some kind of misconduct, the state might come after you for money. This can be accompanied with or without some sort of supervision, such as an obligation to check in periodically with a court officer, or to present oneself for a drug test, or to call an office or something like that. Then there's something called a cash bond, which means that in order to achieve predisposition release, the defendant must deposit some money with the court, and the court will, pursuant to a legal proceeding, have the ability to seize the money and keep it if the defendant engages in some kind of misconduct, predisposition. And so that is why it's called cash. You have to put down some cash in order to achieve predisposition release. And finally, in some jurisdictions, the judge has the option to simply remand the defendant, which means the defendant simply cannot put up any amount of money. It's equivalent to an infinite bond. In other words, the defendant is simply sent back to jail in order to await trial or disposition of the criminal case. There is no constitutional right to a defense counsel present, although in this particular jurisdiction, both the prosecutor and defense counsel were present in the live hearing. The key point here, perhaps the biggest point, is that this decision is made quite quickly and based on limited information. So it's within hours of the arrest. There hasn't been time to do a tremendous amount of investigation into the defendant's circumstances. Typically, what you can do is pull some administrative records on criminal history, and the decision is typically made, a judge typically makes a decision between 2 and 3 minutes per case. So the judge will aim to get through approximately 20 or so, maybe 15 to 20, sometimes more, defendants per hour. And so this has to be a very rapid decision. In this particular jurisdiction, Dane County, Wisconsin, that gave rise to the data that's used for this demonstration of the methods developed, the remand option was really not legally available. It was technically available, but in the state of Wisconsin, which includes Dane County, there were very, 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 very few of these remands because of the procedural burdens that a prosecutor had to go through in order to try to do a remand and try to get a judge to do a remand. And so that's really not an option. There was no instance of it in our data set, nor did we expect any. So the risk assessment that we're going to be using as the example in this particular study is something called the Public Safety Assessment Decision-Making Framework System, so PSA DMF system. Many people call this for short the PSA. It's actually, the PSA is a separate part from the decision-making framework. So the PSA is itself the predisposition risk assessment instrument. It's the one that it's the piece that has the scientifically developed information. It was developed through funding from what used to be and what still is the Laura and John Arnold Foundation, but now doing business largely as something called Arnold Ventures, which is a philanthropic organization attempting to improve criminal justice processes, among other things. The PSA itself associates variables observable at arrest with 3 in particular outcomes that are to be avoided or to be minimized. And those are FTA, failure to appear, and then new criminal activity, meaning in this particular instance, new crimes or an arrest in between the initial release decision and case disposition. So the timing is important as well. And then in particular, new violent criminal activity. So the acronyms there are FTA, NCA, and NVCA. I'll show you the 9 inputs that the PSA system uses in just a moment. The PSA involves two 1 through 6 risk assessment scales for the FDA and NCA, where 6 indicates the highest level of risk and 1 is at the bottom, plus a 0-1 NVCA flag, where 1 indicates an elevated instance of risk. The decision-making framework, the PSA, just to clarify, is designed to be constant and the same across many jurisdictions to be used in the United States. So it doesn't change from jurisdiction to jurisdiction. The decision-making framework incorporates the objective information from the PSA along with other things in order to produce a recommendation for the judge. And so it does change from jurisdiction to jurisdiction. It's designed to, because it reflects the jurisdiction's values. These are I'm going to show you the 9 inputs to the PSA system. They're right here. They are all based on criminal history. That was something that the foundation, the Arnold Ventures, and the scientists involved in the construction, I was not one of them, involved in the construction of this system, were aiming for. They were hoping to produce a metric that could be used based entirely on criminal history and a minimal use of demographics. The only use of demographics is age at current arrest. So the data from this particular illustration of the methods comes from Dane County, Wisconsin, which is, for those of you who have visited Madison, Wisconsin, a gorgeous place, although a somewhat bitter one at this time of year. Basically, the way it used it was that it provided the printout that included the information from the PSA DMF system to commissioners, that's what they were called, deciding the initial release decision. It was also available to the prosecution and the defense. It was somewhat costly to implement, not in a huge sense, but there was some cost associated with it, in part because it requires the gathering of criminal history information from systems administered by different states, and in some cases by different counties, none of which is designed to talk with each other or to be quite frankly, easily accessible to the public. So these are what did we do here? Randomized studies to try to evaluate whether the implementation of the PSA DMF system is something that is worthwhile to the county. Is this something that it should do? Is this good? And so we did that. We basically said that in each case, we would randomize whether the case in each had the PSA DMF system printed and present in the courtroom, or not printed and present in the courtroom. And then we would follow the outcomes. In particular, these were the outcomes that the county and the foundation and I were particularly interested in. The ones that I identified earlier, that the PSA DMF system is designed to target the FDA, NCA, and NVCA, along with the idea of the number of days of predisposition incarceration in particular, and measures of racial fairness. If you think about it, one way to think about this is as a multidimensional minimization function that the commissioner is attempting to implement. The commissioner is simultaneously attempting to implement and minimize the occurrence of all of these, say, 5 outcomes and maybe some others. And the FDA, NCA, NVCA, and even measures of racial fairness, for that matter, could be minimized simply by incarcerating everyone for the entirety of the predisposition period. But then you run into the problem of that you're attempting to minimize the number of days of predisposition incarceration. And so that is the element that is essentially pushing back on that very hard because of the social and fiscal costs associated with predisposition incarceration. This is a timeline of the studies. This particular study, there are others going on in other jurisdictions at various stages of development. This is the timeline. As you can see, as is typical from a field RCT, it's slow. It takes a long time for outcomes to develop. And we just now completed the follow-up period in which we're collecting outcome data. And so we are attempting to obtain the outcome data from the county. That's the work that we're doing right now. That's the final outcome data. The particular data for this study come from 1 year of randomization and 1 year of follow-ups. There were 30 months of randomization in this study. The data for this illustration come from the first 12 and the first 12 months of follow-up. So it's really, in some sense, only about 20% of the data that we would do. Question that we'll talk about just to get this out of the way before I turn things over to Kosuke and for a further extension. Did the randomization work? And basically, these are just basic randomization checks. These are randomization checks to see whether the randomization, in fact, did well in balancing observable background variables. And the answer is it largely did. That these background variables we can observe on misdemeanors and felony distributions on the PSA scores themselves, which were calculated in all cases. Remember, the randomization is not whether to calculate the PSA score, but whether to provide it to the commissioner. That those look relatively balanced across the two groups. The percentage of cases with the violence flag, again, looks relatively balanced. And this is all information that you would expect to see when the randomization did what it was supposed to do. Gender and other demographics look like they're balanced. Ethnicity looks relatively the same. And again, I won't dwell on this. So preliminary results, again, of this preliminary data, it's only preliminary in both senses. One thing that we won't be discussing in the primary paper presentation is the question, did the presence of the PSA DMF system alter commissioners' decisions? And the short answer is that it appeared that it did somewhat. There is a mild shift in accordance with the PSA, PRAI is an acronym meaning predisposition risk assessment instrument. So it's a general term of the class for a class of instruments that the PSA DMF system falls into. There's a mild shift in accordance with the classifications. Actually, prediction's not a good word. It should be classifications. There was a strong reduction in variation across the decisions caused by the presence of the decision. That's something we didn't expect and weren't looking for. So we're still trying to study it. But the mild shift in accordance with the PSA DMF recommendations. I'll just show you that briefly before concluding here. This is a heat map, and the way to read this is to say that the y-axis graphs the score on the NCA dimension, the new criminal activity dimension. Recall that FTA, failure to appear, and NCA, new criminal activity, receive a score of 1 through 6, where 6 indicates elevated levels of risk. And we've basically cast the commissioner's decisions into 3 categories. One where there is a signature bond or OR release, which is really the same thing. One, and these are on the x-axis, one where there is bail imposed of less than $1,000 and one where there is bail imposed of more than $1,000. This is roughly a median amount of cases for which bail was imposed, roughly speaking. And what you expect to see here is what we do see, in the sense that there is some shift here. The way to read this heat map is that if you look across the row for, say, NCA score equals 3, you will see that in the category that of signature bond increased by 8 percentage points, and the category of bail less than $1,000 decreased by 8 percentage points. Again, the percentage points here within the set of folks who had the NCA score of 3. So it's normalizing across the NCA score of 3. So there is a shift from the bail less than $1,000 to the signature bond of 8 percentage points. And there was no shift whatsoever in the fraction of cases that received bail of more than $1,000. That's the way to read this graph generally. And the lines indicate statistical significance of the shift. The bolding indicates, if I recall this correctly, the bolding indicates a shift of a point significance of a p-value of less than 0.1. The bracketing around it also indicates that the p-value is less than 0.05. And you can see that in general, the presence of the PSA DMF system resulted in a shift in cases classified by the system as lower risk to the left, and the presence of the system generally resulted in a shift of cases classified as higher risk to the right. Not all results are statistically significant. Remember that we don't have the full data. We only have half of the data, or actually not even half of the data, 12/30ths of the data that we anticipate getting. But it looks like this is a shift that would be what we would expect. There are the usual caveats here. There's lots of data to be collected on this. And at this point, I will turn it over to Kosuke for further review, if I can figure out how to exit. Let me see if I can do that.
Okay. Thanks, Jim. I think we should pause, and then if there are any questions from the audience about what Jim just discussed, maybe you can answer that question.
Yes, we would like questions to be asked in person, or if you prefer in the chat box. Please, can I just ask people not to turn their video on? Only if you are speaking can you turn your video on. So, are there any questions for James?
Looks like Jane Hutton.
Yeah. Your final slide might have answered a question I had. Throughout, you talk about the judge's decision. And to me, this, in any situation in which you've got a human decision maker, you should be thinking of a cluster randomized design where you're comparing variation within and between judges. So did you have one single judge for the whole county?
In this particular, yes. In this particular study, there was only one judge. In other studies that we have done, there have been more judges deciding, and we in fact suggested just what you did, or variations of just what you did, and the jurisdictions with which we are working declined to implement those designs on the ground that they were simply too complicated. So we don't. I agree with you that. There is a danger of, and this is perhaps where you're headed, of some potential learning or spillover effects. But in other jurisdictions, we do have multiple judges. We have not yet been able to implement something that more sophisticated randomization scheme, and I can explore that with you. There were ideas I had about potential double randomization or where you would randomize judges to whether the PSA DMF system was present in all cases, some cases, or no cases, and then within the ones where it was available in some cases, randomize for them, obviously, whether the PSA was available in some or none. But we were not able to implement those as a matter of field complication.
Great, yes. Very interesting question about how to do it.
Thank you, Jane. I see Maria Quella has a question. Maria?
Yeah, just a clarification question, Jim. So you said the PSA scores were the same for all the country, but that the algorithm is the one that changes. So who designed the DMF section of that algorithm? Was that you guys?
No, definitely not. We were not involved in any aspect of the design of this at all. We were called in as external evaluators, basically. The DMF, the design of the DMF basically came in terms of the things to be considered. Was a suggestion from the combination of the foundation and the scientists that developed the PSA scores themselves. the particular values to include in the DMF system varied from jurisdiction to jurisdiction. So an example of that is that there is the way that the DMF translates the PSA scores into a recommended decision is that it produces a grid, a 1 through 6 grid based on the FTA and the NCA, and then you can imagine a diagonal in which 6 would get a recommendation of the most serious supervision, the highest bond amounts, or whatever it is. Although the PSA doesn't actually make a bond recommendation. Anyway, the highest level of supervision and conditions, etc. 1-1 would be the opposite. Certain combinations of scores are impossible because the inputs are common. Some of the inputs are common across both scores, and so there's certain portions of the extreme ends of the corners of the grid that are not numerically possible. And it basically, you then create the grid, and then there are bands, there are color bands that are presented to the judge so associated with this score, what are the levels of supervision that are available in the jurisdiction? Because jurisdictions vary according to whether they have things like ankle bracelets, for example, or whatever. And so basically the jurisdiction associates, among other things, where the color bands fall, because it may, there isn't maybe an ankle bracelet category in that jurisdiction because they just don't have that program. It's expensive to run. Or a call-in program or something like that. And so how many colors and where those colors fall varies from jurisdiction to jurisdiction. And so that's one example. There are others of the ways in which jurisdictions' resource constraints and, quite frankly, tolerance for risk varies. In this particular jurisdiction, Dane County, they had a relatively high tolerance for FTA and the FTA for failure to appear. And they basically took the view a little bit more towards the view that failure to appear was an information and social problem more than a willing thumbing your nose at the criminal justice system problem. And so they tolerated a little bit more of it. And there was more of it than we've seen in other jurisdictions.
Thank you.
Yep.
I have a question too.
Delighted.
Okay, so if the different individuals are sharing the same judge, are you assuming that their decisions are independent or not?
Yes, in this particular application,
and how
we
can
know
you assume they are independent if it's the same judge making the decision?
We know that assumption is perhaps a strong one in this context, and it's something that we're working on with to extend with future work. It's also one of the reasons why we, at our recommendation, the foundation funded us to do multiple RCTs in different jurisdictions where there are more than one judge. And so the one thing I will say is that this particular judge that made almost all of the decisions was interested in separating decisions as much as possible. It is possible, however, that the judge was able to internalize the inputs of the PSA DMF system and potentially mentally calculate what the scores would have been over time. And so that's what I mentioned earlier about the learning effects in the single judge, and that's why we are pursuing and will be producing results with this team based on other RCTs in other jurisdictions that had multiple decision makers.
Thank you. Are there any other questions for James? Otherwise, I think we can move on to hearing Kosuke.
Okay,
Okay,
great.
thank you.
Yeah, thanks, Jim. Just a couple of comments on the questions, the important questions people asked. Jim and I and other team members been working on different designs of randomization, how that impact the inference we draw. There's also interesting questions about PSA DMF system. Can we improve upon those systems by changing those scoring systems a little bit? And there's a paper on my website that sort of tries to do some of that. So if you're interested in those issues, I encourage you to take a look at some of those work. Let me share my slides for talk. Is this working okay? Okay. Assume it's working. So
yes, we can see the slide.
okay, good. Thanks. Yeah, so the demo meeting is supposed to be providing some background information for the main meeting. So I was thinking what I could discuss and thought about something we don't really discuss in the main presentation that we'll have this afternoon or this evening, late afternoon in England time. So this is about issue of fairness, and any type of experiment like this would one would consider thinking about what are the fair decisions, whether it's algorithmic or human, or in our case, algorithm-assisted human decision making. So I wanted to sort of talk a little bit about this issue, and it's based on a paper, joint work with Jichao Jan, who is I think present online. He is also part of the author, our team that does the main presentation this later today. Okay, so fair decision making. So what is a fair decision? That's a really difficult and important question. Obviously, there are a lot of philosophical issues and other ethical issues that are involved. So there's no single answer to this. But if we come up with several definitions, alternative definition of fairness, how do we assess using the data the fairness of a particular decision? So that's a very important and interesting question for statisticians. How should we improve the fairness of decision making using the data? That's also, once you agree upon several measurement metrics of fairness, how do we use the data driven improvement of those decision making process? So there are lots of examples that includes, court decisions. That's a topic of our study, but also in medicine, where physicians make certain decisions, college admissions, renting, financial renting, mortgage renting issues, insurance premium calculations, and hiring. And in all these decisions, often nowadays is based on the data and algorithmic recommendation. The issue of fairness is extremely important. In my sort of own research, I'm interested in fair decision making in public policy sphere. So these are high stake decisions often made by judges, politicians, and other actors. And I think here the fairness is even more important to consider. And there's, as many of you probably know, there's a literature on algorithmic fairness. And the presentation that I'm going to give you now is based on the following paper that's available in the archive. All right, so before I sort of discuss the specific fairness criteria we are considering, I want to review some of the stuff that's in the literature. That's I call them statistical fairness criteria. So these criteria have been developed for assessing the fairness of prediction algorithms. So whether that certain prediction algorithm provide a fair, classification of predictive outcomes, but they are also used for assessing the fairness of algorithmic human decision. So as I discuss later, these two things, the fairness of prediction and the fairness of decision, I think needs to be separated. But these statistical fairness criteria I'm going to describe have been developed for assessing the fairness of prediction algorithm, and then that's being also used for assessing the fairness of human decisions, whether it's algorithmic or human. Okay, so in terms of setup, let Y denote outcome. I'm going to use the D for prediction or decision, depending on what you're trying to evaluate. And there is some protected attribute, like race or gender, I'm going to denote by A. Okay. So the three statistical fairness criteria that you will see in the literature are the following. The first one is a very simple one, the equal decision. So this means that the probability of, say, if the decision is binary, then the probability of decision doesn't depend on the protected attributes. So regardless of your racial category, the decision will be given similarly. The second criteria often used in the literature is called equal accuracy. So this is a conditional independence between the decision and attribute given the outcome. So the idea is that in the prediction case, the prediction should be equally accurate. So probability of d equal 1 should be, given the y outcome is actually equal to 1, should be the same across different ratio groups. And similarly for the outcomes y equals 0, the prediction should be equally accurate across different ratio groups. Okay, so the criteria is equal calibration. So the decision of prediction is equally calibrated. So this is conditional on decision, the outcome, and then attribute are independent of one another. So across ratio groups, given the decision was 1, the outcome should have an equal probability distribution. So these three criteria are often used in the literature to assess the fairness of prediction algorithm and sometimes the algorithmic and human decisions. Okay, so bringing back this to the criminal justice system, there is a very well-known debate that's involving something called COMPAS. This is correctional offender management profiling for alternative sanctions. So this is another sort of algorithmic recommendation for judges. And there was a famous article by ProPublica that was basically, made it aware that there might be a potential for racial biases in this type of algorithm that's been used in the United States criminal justice system for a long time. So here's sort of a picture from that article, and they show that there are two arrestees who basically committed the very similar crime, petty theft in this case, but African woman was rated by this algorithm as high risk, whereas the white man was rated as low risk. Just to remind you that this COMPAS score is different from PSA score that we will be evaluating in the main meeting, and just the thing that Jim discussed. There's another example here that the two drug possession arrests, again, the African-American man is rated as high risk, and whereas the white man was, committed a similar crime, was rated as low risk. And the article sort of points out that if you compare Black defendants' risk score, which is on the right, with the white defendants' risk scores, which is on the left, you see that the Black defendants tend to have higher risk scores that is classified as more risky than the white defendants. So what's in, sort of this debate generated some of the algorithmic fairness literature, and one of the important set of results that were obtained in that literature was something called impossibility results. So ProPublica pointed out that false positive rate is much higher for Blacks. So what that means is that if you are Black and suppose you aren't rearrested, but you tend to be rated much more riskier, as risky by the COMPAS score when compared to the white people. Okay, so ProPublica thought this was one way to think that COMPAS algorithm is biased against the Black people. Now, the people who developed this algorithm came back and said, well, actually the calibration is roughly equal. So whether you're Black or white, if the algorithm rates you as risky, then the probability of rearrest is about similar. So the COMPAS score itself is really not biased against any racial groups. Okay. So the question is, how do we reconcile these two different arguments and evidence? And it turns out that you might imagine that it is impossible to satisfy both criteria unless recidivism rate and the score distributions are identical across racial groups, which in this case they are not, or some racial groups never experience recidivism, which in this case is false either. So it turns out it is possible, based on different fairness criteria, you can reach different conclusions based on the same set of the data set. Okay. In the literature, you see the results, several related results. In general, we can't satisfy all three statistical fairness criteria I described at the same time. For example, if equal decision and equal accuracy hold, then either the base rate is equal or the decision is useless, that it's not correlated with the outcome at all. Similarly, if the equal decision and equal calibration hold, then the base rate has to be equal. So these results are available in the literature, sort of trying to understand the relationship between different statistical fairness criteria from mathematical point of view. Now, what I want to sort of today argue is the statistical fairness criteria that I just described actually ignore the fact that the decision may affect the outcome. And this may be okay if it's if you're evaluating the fairness of predictions. However, to the extent that if you're evaluating the fairness of the decision, we really should take into account for the fact that the decision may actually influence the individuals. And even if you are evaluating maybe accuracy, the fairness of algorithmic recommendations, to the extent the algorithmic recommendation may affect the human decisions, like in the case we study, we really need to concern about how the decision actually affect the, the algorithmic recommendation affect the outcome downstream. Right. So the other issue is that if the decision affect the outcome, the observed data are contaminated often. So this is in the literature often called selective labels problem, but the data you collect are influenced by the decision. So the outcome is influenced by the decision. So, you have to take into account for that selection problem. And also, I think in general, I feel that the fairness should address how individuals are affected by the decision. And that's maybe part of the reason we want to consider the fairness of the decision, because the decision has a big impact on the individuals' lives. So how do we do this? So what we consider is the causal inference framework, because here we have to understand the causal effect of decision on the outcome. To do that, we're going to use the potential outcomes notation. So y of 1 is the outcome value that would be realized if the decision equal 1, d equal 1. And y of 0 is the potential outcome under the scenario that the decision d equals 0. So you can think of causal effect could be a difference between the two. And as you know that there's a fundamental problem of causal inference. For any given individual, decision is either 1 or 0. So you never observe y of 1 and y of 0 at the same time. And importantly, the potential outcomes, only one of the two become observed outcomes. So y depends on the random variable d, the decision. And so depending on the value of d, you either get to see y of 1 or y of 0 as the observed outcome y. So you can think of the potential outcomes are sort of pre-treatment characteristics, and the decision determines which one of the potential outcomes will be realized and observed. So this is the framework that dates back to Fisher and Neyman. And what we're going to consider is principal strata. So this is the strata that's defined the values of the potential outcomes. So in this case, in the simple binary case, we have y0, y1, the two potential values of the outcome determines which principal strata you belong to. And this framework is due to Frank, Axel, and Lubin in their biometric paper. So the principal fairness idea that we at Jichao and I advocate is the following. So individuals who are similarly affected by the decision should be treated similarly. So in terms of statistical independence relationship, conditioning on the principal strata, because principal strata is the values of y of 0 and y of 1. So it describes how individuals are affected by the treatment. So conditioning on that principal strata, then the decision and the protected attribute should be independent of one another. So here is an illustrative example. So there are two groups, A and B. We can think of it as racial groups. And these are potential outcomes. So here I call this dangerous group, where whether you're detained or released to y of 0, you commit a new crime, NCA. Okay, so this cell is whether you are detained or released, you commit a new crime. So that's a dangerous group. Preventable group is if you're detained, you don't commit a new crime, but if you're released, you commit a new crime and so on. Okay, and a safe group is you do not commit a crime regardless of detention decision. And backlash group is the opposite, so that you commit a crime only when you detain or you're detained, and then you don't commit a crime if you're released. Okay, so you might be surprised, but even if you're detained, people can commit a crime in the prison. So in this toy example, detention rate within each principal strata is identical for groups A and B. So if you look at the dangerous group, the ratio is the same. The backlash group ratio is the same across these groups. So this is an example where the principal fairness actually holds. Okay? So each group within each of these principal strata, you have the same decision probability. Now, this is based on the potential outcomes. Now, if you collapse this into the observed outcome, right? So if you're detained, say d equal 1, you observe y of 1. If you're released, d equals 0, you observe y of 0. So if you collapse this into the observed data will look like this. And it turns out that in each of in this example, none of the statistical fairness criteria is satisfied. So you can calculate each of these three criteria, and then you see that group A and group B have different probabilities or different conditional probabilities depending on the criteria used. So what this illustrative example shows you is that principal fairness criteria, which accounts for how individuals affected by the decision are not necessarily the same as the statistical fairness criteria. So satisfying the principal fairness criteria doesn't necessarily imply the statistical fairness criteria is satisfied. So what is the exact relationship between these two criteria? So you can think of principal fairness criteria is based on the potential outcomes, whereas statistical fairness criteria is based on the observed outcomes. We show that if there's an independence between principal strata and protected attributes, then the principal fairness implies all three statistical fairness criteria. So what this means is that if a certain racial group is not inherently risky, then the principal fairness actually implies all three statistical fairness criteria. If you further assume monotonicity, that is, you're no more likely to commit a new crime if you're detained. So this is what that means. You could commit a crime, but no more likely to commit a new crime. Then you can show that in addition, with these two assumptions, the principal fairness is actually equivalent, rather than stronger, equivalent to these three statistical fairness criteria. So this is similar to the equal base rate condition that was discussed in the literature, but our equal base rate condition is based on the potential outcomes instead of the observed outcomes. And obviously, these results hold condition on the covariates. Now, there's a interesting question about whether one should be assessing the fairness based on some set of covariates, because that selection of covariates have some implications about what fairness actually means. Monotonicity assumption, by the way, implies in my example that it eliminates the backlash group that I described. So people who commit to a new crime only when they're detained. So I wanted to sort of quickly mention other causality-based fairness criteria in the literature. One is something called counterfactual equalized odds criterion. Very similar to what we advocate. It conditions on a natural baseline, that y of 0. So the only difference between ours and this criteria is that our criteria also condition on y of 1 in a binary case. And in more general case, we condition on all potential outcomes. So this distinction we think is important because this existing criteria does not account for the impact of the decision. So it's more the idea of thinking about what's the natural level of risk, as opposed to thinking about how the decision impact individuals and how you define fairness based on that impact. You can show that if this conditional independence holds, principle of fairness implies this criterion. So it's sort of, you can think of the special cases, y of 1 is constant across groups. So in the previous example, if you're detained, everybody do not commit a new crime, then these two criteria becomes equivalent. Okay, so another way of thinking of this is principle of fairness as a generalization of this type of counterfactual equalized odds criterion. The other criteria that's out there based on the causality is something called counterfactual fairness. So here you think of protected attribute as a causal variable. So whether it's a race or gender, you think of the decision is a function of those protected attributes. And then fairness criteria is the decision probabilities should be the same regardless of your race. So this requires you to think about what would happen if you are a different racial group. And there's a controversy about whether that kind of thinking is productive. Some people think there should be no causation without manipulations. Others disagree. So our principle of fairness criteria doesn't think of the race as a causal variable, more on how the decision affect the outcome. So the potential outcome is y of d instead of d of a. So that's a big difference between our criteria and counterfactual fairness criteria. Okay. Finally, I want to just sort of think about how, just to briefly mention, how do we empirically evaluate and do some policy running using this principle of fairness criteria. Difficulty, obviously, is that principal strata are unobserved because not all potential outcomes are observed. It's only one of them is observed. So the approach taken in our JRSSA discussion paper, which will be presented later today, is based on the unconfoundedness assumption, where the potential outcomes is independent of the decision given X. And where X, we call this decision variables. Okay? So this assumption is plausible if the decision variables are known. So if we know all the inputs that goes into the decision, then this conditional independence assumption is credible. So in the case of algorithmic decision, this might be this might hold because algorithm, there's the inputs and then the output comes out. In our case, it's a human, algorithm assisted human decision making. So to the extent that we can capture all the information judge uses, including the algorithmic recommendation, to make a decision, this assumption would be plausible. Under monotonicity and unconfoundedness, we can show that the principal score, the probability of belonging to a particular principal strata, given covariates and the protected attribute can be identified. And then we can evaluate the principal fairness by computing the conditional distribution of decision given the principal strata and protected attribute. We can also do some policy learning, which we don't do in the JRSSA paper, but we are currently working on. You can think about decision as some function of the decision variables. And then we can show that in order to consider this decision rule, how the decision rule relates to the principal strata and protected attributes, you can write this as a weighted average, where the weights are proportional to the principal score. So once you identify the principal score, you can do policy learning subject to some type of fairness constraint, where this probability doesn't depend on the protected attribute. Okay, so let me just conclude. So fairness of human algorithmic decision making, we argue that it needs to be placed in the causal inference framework. That's because we care about fairness of these decisions because the decisions affect people and individuals. So we have to consider that possibility. And there are some important extensions. We're going to look at the algorithmic assisted human decision making. That's our JRSSA paper we'll discuss later today. And we're also looking at a variety of sort of evaluation and policy learning in the real world applications, including this Dane County example that we'll present this afternoon. There are a lot of interesting issues and methodological issues that we could all study. Selection biases and dynamic systems. Often the fairness issues are built on biases that could, that could exist at the various level of, say, in the criminal justice system, from the police encounter all the way to the court decisions. There are a lot of selection issues that would affect the welfare of individuals. And these are all dynamic systems. People are recurring, interacting with one another. And so thinking about more in the, not like static settings, but over time interactions, I think is very, very important. So let me stop it here, and if there's any questions, I'll entertain.
Are there any questions? I don't see any hands raised. Okay. If there are no questions, then please join me to thank both James and Kosuke. Thank you very much.